Good afternoon, everyone, and welcome to today's session on infrastructure. My name is Shane Mott. I'm with Rutgers University Kate, and I will be moderating today. Our first presentation is on the evaluation of performance of bridge decks with ultra-high performance concrete and latex modified concrete overlays through accelerated testing. Our presentation will be given by Dr. Nenad Kuczynski. He is a professor and the chair of the Civil Engineering Department at Rutgers University. With the introductions out of the way, whenever you'd like to get started.
Thank you very much for the introduction, and thank you for the opportunity to speak about our project related to the evaluation of performance of concrete bridge deck with these two overlays. So the first question which we can raise is why it is so important to understand performance of concrete bridge decks. First of all, what we can say is that because of their direct exposure to traffic and environmental loads, concrete bridge decks, they deteriorate faster than all other bridge components. And those who are the owners of bridges, they know how much money they are spending for proper management of concrete bridge decks. The second reason why we are conducting this research is the relationships between the performance of concrete bridge decks and many factors which are listed here. They are still not fully understood, and we have not developed correlations which could help us in better bridge management. And so the question is, so how we can develop better understanding of the performance of bridge decks, but not by waiting 30 or 40 years on real bridges, but in an accelerated manner. And this is what I will be discussing today. So there will be three parts of my presentation. In the first part, I will be just describing how we are doing condition assessment and monitoring of concrete bridge decks using non-destructive evaluation technologies. I will speak about it because those will be essential to describe the results which we are conducting through accelerated testing. The second part will be related to the description of the BEAST facility, this facility for accelerated testing. And finally, I will go a little bit through the results obtained from the testing of both the deck with overlays and the bare deck. So a little bit about how we use ND technologies to do condition assessment and monitoring. So when we speak about what concerns us with concrete bridge decks, and we can say with any reinforced concrete element, these are the issues related to corrosion, to delamination, concrete quality degradation, and cracking. And for example, when we conduct non-destructive surveys on concrete bridge decks, this is how it looks like. We go on the bridge, we mark a grid using a washable paint. Typically the grid is 2 by 2 feet. And then we deploy a suite of technologies. All of those technologies are listed here, but I will be also speaking a little bit about each of those. So approximately what is being done is that by having this team of 5 to 6 students, technicians, collecting data, we can, let's say, roughly collect the data on about 1,000 square feet of bridge deck per hour. To illustrate that they work. So here you can see an example from a long-term bridge performance program we participated in, and we collected data, one bridge in Virginia, which we surveyed 4 times within 6 years. So first technology, electrical resistivity methods, which we use to assess how corrosive environment that concrete is, because highly corrosive environment will relate to high corrosion rates. And here you can see for 4 surveys from top 2009, 2015 at the bottom, you can see those red colors which indicate problems, that there is increase in the areas which are affected by this highly corrosive environment, and that intensity is increasing. Moving to the next technology also for corrosion assessment, something what we say to evaluate corrosion activity, actual activity on rebars, half cell potential. Again, if you would follow all of these maps, you can see from 2009 to 2015, we have expansion of those areas. So corrosion activity progressed. Delamination assessment. For this one, we use technology Impact Echo. And here you can see also those red areas that they are expanding. So those would be shallow delamination, which you could detect in most cases using chain drag. And finally, another technology, ground penetrating radar. That is a technology which we can describe, provides a qualitative assessment. You get an idea about the condition, but it doesn't tell you what is the cause. It doesn't tell you there is delamination, there is corrosion. No, but we know from high attenuation of electromagnetic waves, which are here described by those dark red colors, that there are some issues. So why we are conducting multi-NDT approach? Well, we want to say something about delamination, concrete quality, about corrosion. That is one reason. The other reason is to identify what is the primary cause of deterioration in concrete bridge deck. And here, if you compare, for example, these two zones, and the top two plots represent measurements related to corrosion. You can see here, so below that is the lamination map. We can say that the primary driver in this bridge was corrosion. What you are going to see from our results from accelerated testing, it was not corrosion, it was really concrete quality degradation as a result of repeated live loading. So how we can use this information? We can quantify it, and that is the big advantage over visual inspection. For example, we are calculating these condition indices, where on the scale 0 to 100, 0 is the worst, 100 is the best. And what this condition index represents is a weighted average of percentages of deck area in different conditions. So for each technology, we are calculating condition index. And if you look in this plot, from 2009 to 2015, each of the technologies is capturing the change of the condition. It's moving back. So what I have shown you were the data only for those 6 years, but we always have to think about the life of the bridge. And the life of this particular bridge started in 1979. So we don't have any information between the birth of the bridge and when we first tested it is in 2009. So there are a few questions which we can raise. The first question is, was it really the initial condition something what deserves condition index 100? And as you are going to see, for example, from our testing in accelerated facility, it is not truly the case. And we also know from some real bridges which we tested after construction. The second question is the shape of the curves like it is shown here? And that is what is missing. Here we can be a little bit more comfortable because we have those 4 measurements. But if you conducted only a single measurement, you would probably ask, I don't know how to get from the start to that point. So let me speak a little bit about this facility, BEAST. BEAST stands for BEAST Evaluation and Accelerated Structural Testing. So here you can see it, how it looked like under construction, and the reason is because I can better explain what you do there. So first, what it can do, it can accommodate structures of the size 50 foot long, about 28 feet wide, and about 5 feet deep. You can apply dual axle loading, which can apply loading up to 60 kips. We typically run at 50 kips. And it can do up to 17,000 cycles of loading per day. You can also control environmental conditions in this environmental chamber. So you see what is marked as environmental chamber. So the structure is there. You can control temperature anywhere from 0 to 104 degrees Fahrenheit. And you can simulate winter maintenance by spreading salt brine. And that is what we do. So to illustrate how this thing works, we will start with an animation, and then we will go to the actual bridge. So the structure can be prefabricated. The structure can be prefabricated and just placed into the environmental chamber, or it can be built in place. And our very first structure was built in place. Once it is in place, the chamber is closed. There is this carriage, which is moving, what I said is approximately, we do it approximately 10 to 12,000 times per day. And what is being done also simultaneously, we cycle the temperature. So we need to go to about 0 degrees to cause freezing of the bridge deck. And then if we go up, we can go up to 80 degrees. But the goal is to bring the temperature of the deck back to about 40 degrees Fahrenheit. So here you can see the change in the temperature, right now heating. And as you apply more cycles, you can expect that there will be some deterioration. In a second, you're going to see the carriage, the real carriage, not through the animation. And you will get approximately the feel for how fast it is. So this is the facility. So this yellow part represents a reaction beam. So that dual axle load carriage is moving along that axis. This white part represents the environmental chamber. And in a second, you will see an open chamber with the carriage running. So 10 to 12,000 cycles with a load of about. And what you're going to see at the end is what we did. We're collecting information about the condition so that environmental chamber is fully open, and then we deploy a suite of NDE technologies and we collect the data. The data being collected on a grid 1 by 1 foot. So let's speak about the results which we have obtained on both bare and overlaid concrete bridge decks. So we had two phases of the testing. In the first phase, where we tested bare concrete bridge deck, that bridge deck was put under 2 million passes of live loading. In the second phase, which is still not done, we will probably go up to about 4 million passes. What was done? The original bridge deck was hydro-demolished to approximately top rebar level and was on one half overlaid with UHPC, and on the other half was overlaid with LMC. So this is supported by Federal Highway Administration's long-term bridge performance program. So this is how it looked like when we were constructing. So this is the supporting steel superstructure, girders. This is the finished first bridge deck, and you can see this grid 1 by 1 foot. These are the points where we are collecting information using that suite of NDE technologies. Environmental chamber, so which is closed once everything is in place, and that carriage is running. So in phase 1, you can see that, for example, if we did not have interruptions, and we had interruptions for various reasons, from COVID to some pieces of equipment needed repairs and so on. But those 2 million passes, if there was uninterrupted operation, it would be about 150 days. And during that time, we have also applied approximately 120 brine applications, and that bridge deck went to about 100 freeze-thaw cycles. That carriage is not moving only in one position, and here you can see. So that beam is moving laterally, and you can see, for example, what was the distribution after 1.5 million of passes. So pretty much, you may say, except for the edges, pretty much every part of that bridge deck experience is loading. This just illustrates those cycles. So to achieve this cycling of bridge deck temperature between 20 and 40 degrees Fahrenheit, we have to change the temperature in the chamber between 0 and 80 degrees. Again, we are using a suite of technologies, and these are the 6 technologies which are of primary interest to us. So they help us evaluate to monitor concrete quality degradation, corrosion, and also delamination. So to go back to what I mentioned earlier, the importance of baseline measurements. For example, when this bridge was constructed, there were 4 truckloads of concrete. And they're marked 1, 2, 3, and 4. We took also some cores and measured their modulus, but we also used a technology, ultrasonic surface waves, to measure modulus of concrete. And what you can see, there is significant variability in that modulus. So there is good correlation between what was measured on the cores and on the deck itself. So don't expect that you will have uniform material. Far more important element for this baseline measurement was concrete cover thickness measurement using ground penetrating radar. It was supposed to be 2-inch concrete cover. And as you can see that in the middle, it was only about 1.25 inch. So even though this was experiment, it was known that it was going to be research. It seems the primary cause of this variability was the placement, the support of the screeding machine, which caused a little bit of this bending of the girders and ultimately to reduced concrete cover. And as you are going to see from the results, that low concrete cover will be very important for observed deterioration. So just to illustrate what we would do is, for example, within phase 1 for bare concrete deck, we conducted about 15 ND surveys. I'm just showing some of them to show that we are capturing the changes. For example, at this map, where you start seeing these yellow zones at 360 days, low modulus, we know from previous experience, these are actually signs of initiation of delamination. And that really happened, so those zones, which are in red, later delaminated. To illustrate how we are capturing this is an animation. Before I start it running, I would like just to explain what you should follow, because it's a very busy animation. There are 4 maps. So the top one, corrosion activity, and the second one, condition assessment from GPR. You can say that those are mostly related, you may say, to corrosion activity and corrosive environment. And because both of those are affected by environmental conditions, for example, moisture content in the bridge deck, which is changing, you will see that it might look like it goes worse and then it goes a little bit better, so improvement. And this has nothing to do with the condition of the bridge deck. It is the effect of the change of environmental conditions. At the bottom, you can see concrete quality map expressed through concrete modulus, and bottom right represents delamination. On those, you cannot improve concrete quality, you cannot improve delamination. You will see continuous degradation. What you will see on the right side, you will see where were the passes of that truck, of that carriage, and at the bottom you will see how different those applications of temperature changes and also brine applications when they were applied. So let's start with the animation. So it will show in total 850 days. So the moment you start seeing warm colors are indication of problems. You can see, for example, in the middle, half-cell potential is starting to show some corrosion activity. Again, it may weaken a little bit because of the change in environmental conditions. You can see on concrete quality map, these yellow zones, indication of initiation of delamination. Ground penetrating radar, higher attenuation is also an indication that there are some issues. And as concrete quality is degrading, you can see on the bottom right map that delamination is forming and is progressing. And let us remember, this middle section had thinner concrete cover. So this definitely contributed to faster acceleration, faster degradation in the middle section. Okay, so here you can see, for example, some degradation curves for the bare deck. So what we can see in general trend, we did not want to go too far because we wanted to use the same bridge deck for the second part, for phase 2, evaluation of the performance of overlays. So what is always important to do is to compare different segments, and this is what we have done in the past, whether it was a big bridge, where we segmented bridge to evaluate, provide assessment of different, not just the whole bridge, or if there were multi-spans. So in this particular case, for example, we have divided into 10 segments, and we can just concentrate on, for example, these 3 segments. If you look at red and blue curves, which represents delamination assessment and concrete quality degradation, you can see that in the middle section, those condition indices have a significant decrease, while on the sides, there was far less degradation. So concentrating on that middle section of the bridge deck, we can look into, for example, delamination progression. So on this bar chart at the bottom, those different parts represent sound part, something what we describe as fair condition, and something what we describe as a serious condition, which is typically shallow delamination. And you can see that it is expanding, something what we can also see that significant progression of delamination started when we had more intensive live loading. Very similar for concrete quality degradation. We are using 2 measures. The first one is the change in average concrete modulus, and the other one, even more important for to detect concrete degradation, is standard deviation. And if you look, that there was a significant drop in the average modulus, and equally there was a significant increase in standard deviation of that modulus. These are clear signs of concrete quality degradation. Now let us compare the results of bare deck to the deck with overlays. On top you can see what was the image of that bare deck after 2 million live loading passes. At the bottom is the image of the deck with 2 overlays after 2.6 million passes. As you can see, while you can observe spalling on the bare deck, there were no signs of spalling on the overlaid deck. Some might say, well, it could be primarily a result of a thinner concrete cover on bare deck. Well, we measured also on the overlaid bridge deck, and that overlay, again, concrete cover was maybe 0.05 inches thicker than it was on the bare deck. So they have pretty much the same conditions with respect to concrete cover. And here are just some comparisons. on top, you can see, for example, the lamination map from Impact Echo and corrosion activity map from half cell potential. So top two maps are for bare deck, and those were after 2 million passes. The bottom two plots are for the overlaid bridge deck with 3 million passes, so 50% more live loading passes. And what you can see with respect to delamination, there are no signs of delamination in the overlaid bridge deck. Similarly, there are no signs of corrosion activity in the overlaid bridge deck. From two other technologies, ground penetrating radar and electrical resistivity, which in great part describe corrosive environment. As you can see, clear signs, so red colors indicate problems, while for the overlaid bridge deck, we can say is that resistivities were extremely high, and in general, we can say there was very little attenuation from GPR. Comparing concrete modulus degradation from ultrasonic surface waves, again, we are comparing two maps. On the left is bare deck after 2 million passes. On the right is for the overlaid deck with 3.2 million passes. So here you can see, first of all, is we are measuring different modulus for UHPC and LMC. UHPC is a significantly higher modulus. And you can see that average modulus is very steady, and there was very stable standard deviation, which I mentioned previously, is typically an indication of concrete degradation. So it was very stable. On the other hand, when you look at the bare deck, that standard deviation was going up and average modulus was significantly decreasing. And finally, if we compare the lamination assessment, you can see condition index for the overlaid bridge deck was very stable, about 90. On the other hand, blue line for the entire bare deck, it was decreasing, and it especially decreased for the middle section, so which dropped down to about 60, the condition index. So just to make a few conclusions, so what we can say is that that this bridge deck with overlays has shown significantly better performance than bare deck, and that even with 60% more live loading cycles, there was lower concrete quality degradation, and there were far less signs of corrosion and delamination. And this is in a way telling us is that we should think about not just using these ultra high performance, for example, concrete overlays for rehabilitation, but that we might think and newly constructed bridge deck finish them with UHPC. What we have done is what we have estimated with respect to live loading. We, for example, estimated that 1 year of operation of BEAST facility would be equivalent to about 106 years of truck loading on that Haymarket Bridge in Virginia, which I showed at the beginning. So this facility dramatically accelerates testing, and we should use it to develop a better understanding of deterioration mechanisms and progression in bridges. So something what I mentioned is we looked into those equivalent load factors, and we estimated that probably we are accelerated real truck loading effect in terms of damage creation 30 or more times faster than what you would have on 90% of real bridges. What is critical for better bridge management is by having this ability to collect data, that this puts us in a position to develop more realistic deterioration and predictive models, and ultimately use those in bridge management. And while we have demonstrated here how we can use accelerated testing to evaluate performance of concrete bridge decks, the facility opens opportunities for so many other things, like evaluation performance of some other new materials, new designs, to assess performance of and capabilities of different condition monitoring and assessment systems, to evaluate the effectiveness of different maintenance and rehabilitation procedures, and so on. So I very much appreciate your attention, and I will be happy to answer any questions. Yeah.
Actually, I'm Avinash Prasad, Administrative Engineer from New York City Department of Transportation. I work for the Bridge Division, and I do bridge inspection. So I'm very excited about this presentation, the way it was presented. My only question is that the way our bridge decks is deteriorating right now. And the kind of innovation the presentation, your presentation shown today, how cost effective it will be to make into the transition into this one, because even some of the new bridge decks were installed, still we are going with the conventional bridge deck.
Yes.
So how much cost effective it will be for our coming bridges? I mean, coming bridge tops, we can think of doing this.
Well, I'm not in bridge management, but how I'm viewing is it might be, you probably should look different bridges depending on what is the traffic amount. So, for example, if you have a bridge which is on a highway which has very high ADTT, and you would like, for example, you know that you will likely have to do some work on that bridge deck after 10 years or 15 years. Yeah. And you can imagine what kind of benefits it would be if you could extend it to 25 or 30 years. Yeah. And so what we have done is, and what we do in the BEAST facility, we are primarily, while we are changing environmental conditions, we are primarily evaluating the effect of live loading. Because for environmental loading is, for example, when you speak about corrosion. Corrosion is not just if you spray more salt brine that you are going to accelerate corrosion. Yes, you will, but it is also a function of time. Yeah. Yes, you are like you have a function you have to integrate to get cumulative effect. Yeah. How much corrosion you are going to get. So again, you know, the benefits are going to depend on how much traffic you have, how frequently you would need to do maintenance or repairs, how much it is going to have indirect cost by interrupting traffic. So there are many elements, and I would say those who are in bridge management, they probably can speak very well, you know, what would be the costs and benefits of placing overlays.
Okay. Thank you.
So is this facility only for concrete or asphalt layer on top of the concrete?
No, you could place any overlay. Yes, you could place any overlay. And so we don't know what is going to be. This phase of testing is going to finish in March or April. And then we are going to see what is going to be next. Sandy.
Bridge deck, how much time will it take? 6 months or 1 year?
Well, this structure has been now 5 years. Yes, it has been about 5 years in place, yes. So if there is no need to replace the whole structure, if you can use the original bed, that original deck, there is no reason why not to conduct another experiment. Okay, thank you.
Thank you, Dr. Kaczynski. Okay, yeah, we're running a few minutes behind, but we're still on schedule here. Okay. So yeah, to get started on our next presentation, we have complex simulations of large ship impacts on bridges. Presenting today will be Dr. Anil Agrawal. He is with the City College of New York. And feel free to get started whenever you'd like. Okay.
Thank you very much for the kind introduction. So, you can see I'm going to talk about large ship impacts. And if you think what happened in March of this year, the collapse of the Key Bridge in Maryland. And this presentation is kind of like focused on that, what really happened in Maryland and what really we can do. We had a workshop, I organized a workshop on August 7. It was a virtual workshop from people around the world. We had around 700 participants online from all around the world. We had 10 speakers. A lot of discussions on this topic about what we really need to do. So this is a broad outline of what I'm going to talk about. Collapse of the bridge, current ISO guideline, and what really our options are, what is the best approach I think we should be going moving forward. So let's just start with the Key Bridge. What really happened that day was that the Dali ship started, and you'll see in a minute that ship is starting from a port side, and it's you can see here it's moving slowly. And as it's going, I will just, we have the bridge here. So let me move it forward. It's, you can see the speed, knots, and then, hold on. So, see, there you go. The bridge is in sight now. This was a live camera there, which was recording the whole event. You can see the ship heading for the pier. Fortunately, you can see there's a lot less traffic. It was not just coincidence. There were 3 minutes. In 3 minutes, there was a lot of activity between the control room of the ship and the Coast Guard that alerted the police that the ship might impact the bridge. Bridge will collapse. Police started closing the traffic. So there's very few traffic on the bridge. And, you can see it's almost near the bridge, and you can see one of the trucks is passing by. It cleared. There were 6 workers on the bridge who died, unfortunately. Very tragic for them or their family. And eventually, the ship went and struck the bridge, and the bridge collapsed. And we know very well what really happened. But was this the event? It was a pure accident, or could have been prevented. So, if you look at the history of the bridge accidents in USA, particularly the bridge collapses because of ship impact, all the accidents worldwide, almost 50% of these incidents that have happened in USA, which is very remarkable that naval traffic is so massive and we have so many bridges around the world, but we have a majority of the bridges are collapsing in USA. Let's see what really was the cost of this collapse. $1.5 billion at least, the rebuilding cost of the bridge. If you look at the economic loss, if you assume 11.5 million vehicles per year, then you are looking at close to $9 billion loss. There are 4,900 trucks which have to now do 30-mile detour, increased accidents, air pollution, loss of use, port facility, loss of business. Altogether, the estimate cost is close to $20 billion. So, was the Dali the biggest ship? Well, if we look at the size of the ships, and you can see here that relative size, this was MV Dali. This is the world's largest ship. And if you want to imagine, this is your Empire State Building. So these ships are as large as the Empire State Building. In terms of container capacity, you have seen those containers, 20-foot container. Dali could carry 10,000 containers. The largest ship right now can carry something like more than 20,000, 25,000 containers. In terms of size, you can see how the size has been growing from 1980s. I'm referring to 1980s because that's when the accident happened and ASTO really started, developing the guideline. This was here, 1980. We are here now. This is just 2020, that you have 24,000 TEU, means 24,000 containers that could be loaded on one ship. In terms of weight, well, we know Dali was 116,000 ton, but real weight, which is what is important for us, was actually 150,000 ton, because that DWT that we hear, 116,000, that's the capacity to carry the containers. You have the weight of the ship itself, another 20%. So if you add everything, we are 150,000 ton. That ship, when it impacts, it applies a force of 50,000 keps force on a structure. It's massive force. But was that the only accident? Well, just 2 months before Dali, on January 29, 2024, a ship called Ship and May, it collided with the piers of a major bridge, Jarato Brazos Bridge in Argentina. So let's look at the comparison. The Ship and May, 220-meter length, Dali 229, 36, 36. And May had around 85,000 ton load at that time. And Dali ship had 116,000, but Dali also unloaded the cargo in Baltimore. So probably these two ships had around the same amount of cargo or weight at the time of accident. This ship, you can see you have the bridge there, and the ship goes and hits actually the pier. But fortunately, it did not hit the pier. Around the pier, you had this pedestal, and ship got stuck into the pedestal. The pedestal pierced right through the side of the ship, and ship got stuck. The thing is, the bridge did not collapse, although the impact force was almost similar to what we had during Dali, which really tells us that around the Maryland Bridge, if there was a platform, protection, a fender, what we call in bridge engineering, the bridge would have survived. We would have saved $20 billion. We would have saved those people who died there. So how are we progressing? Well, the whole research on ship impact on bridges started after this Sunshine Bridge, very similar to Key Bridge. The Sunshine Bridge was impacted, and that was a 33,000 tons carrier. And the carrier hit, the bridge collapsed, and it led to the research on the ship impact, and ASTO had massive activity. And finally, in 1991, we had a code in ASTO which could account for ship impact on bridge piers. But where do we stand? Well, I'm showing you this chart where there has been a lot of research. If you see this blue curve, this is the crushing force. So when the ship hits the pier, how much crushing force is applying? So this is ASTO, and very smooth curve, because the ASTO curve is very, very smooth. And this is a research by Professor Peterson, and this is very old research based on the ship class, which is a much stronger ship. And we don't have all those ships all the time coming in our port. But Professor Peterson recently also did some more work, and he has this model, and this is very realistic model based on how much energy is dissipated and how the ship is crushed, the bow of the ship, and force. If you look at here, the Dali was 100 something beyond this 100,000 ton. So what you are looking at, that even you design the bridge piers or protection for ASTO, you're still, the actual there's a big difference, almost a difference of 50% or 60, 70% sometimes. Really depends. If there's side impact, the difference could be much bigger. So the whole point is, we are designing by the ASTO, but ASTO code really doesn't, give us the full picture that whether we can present the bridge completely. Again, if you look at the length of the ship, this is the length of the ship versus the crushing force. You see here we have up to somehow matching here, and then this goes off completely. The Dali ship was here. The big difference in the crushing force. The reason is because we calibrated our model based on the barge impact and all those things in 1980s accident, and it's really based on the load capacity up to 30,000 tons. So, if you see in this region 30,000 ton, we have pretty good matching, with some margin of safety and everything. We are pretty good here. The time we get out of this domain, this starts shooting up because there's more and more crushing of the ship and the weight and everything and length. So, the whole picture starts changing about what really is happening. Other aspect is that ASTO really requires the engineer to calculate the annual frequency. And the annual frequency is meant to calculate whether, do you really need to protect this bridge? Now imagine, key bridge, $1 billion worth of bridge, which could inflict a damage worth of $20 billion. And your repair cost or your protection cost would be something like $60 million. Would you even go and calculate this probabilistic thing to say that I want to see whether this is telling me whether I do something or not? It's understood that, if your assets that, expensive, such impact, then you go and just put that $60 million, put a protection and sleep peacefully that my bridge is going to be safe. So ASTO does this annual frequency of collapse where, it's a function of annual traffic. This is vehicle aberrancy, like when you lose power, the ship goes out of control. Then what is the probability of that? PG, which is a geometric probability, that you have this big channel width and the ship is going and how the ship will go and how far you are from the pier and your probability changes. And PC is that, if the ship did hit the bridge pier, will it collapse? And PF is if you have some protection measures in place. So what we did was we did some calculation for, this is an example bridge, and the example is also already in the ASTO code, where they're assuming the piers have a capacity of 20,000 kips. Dali ship, the key bridge pier probably had around 7,000 tons. We don't have access right now to record because all the records have been sealed. But if we can get the record, we can precisely find out what really happened to, key bridge. But with this 20,000 ton kips, you take all the ship weight, all different kind of traffic. This is the frequency, and you calculate all this probability. And finally, you come to this AF, which tells you that your frequency is 0.0005. And as per the ASTO code, the allowable would have been 0.4025. So it looks like that, yes, you would have been required to do some protection. But that protection would not have been so extensive that it will even protect the bridge for 150,000 ton. If you did protection and decrease this frequency, you would have done some more protection and improve. So maybe from 20,000, you would have gone to 30,000 kips or 40,000 kips, and you would have protected the bridge. But still, with a ship like 150,000 ton, your impact force is 50 or 60 or 70,000 kips force. So it will not protect. But for instance, let's say I went and changed this frequency from this one to I changed the numbers, just playing around with the numbers, fictitious numbers. That you have a lot of these small ships coming and they have a mid-sized ships coming. But one day out of the blue, and the port has the capacity, one day after the blue, one Dali ship came one day and it went out of control. It's possible. When this collapse happened, we had the World Trade Center collapse happening. These are very, very small probability event. This can happen. But the point is, if that happened, are we willing to take the risk? So let's say if I had one Dali ship coming, one day, out of the blue, went out of control, when I hit the bridge pier, it caused the loss of $20 billion. When your repair cost is only $60 million, are you willing to take that chance? Because if you do this frequency, and even you do this calculation, what it tells you that your current pier was good. You have noise, although you have the same pier, 20,000 ton kips, and your force from the Dali ship is 70,000 kips, 60,000 kips. But still, your calculation is showing that, yes, you don't need to actually do anything. That's absurd, because now we are completely relying on some frequency, some freak chance that, even whatever the frequency is there, we are just relying on the freak chance that in future, a ship double the capacity of Dali might come just there one day, go out of control, hit an important bridge, cause the collapse and cause really massive loss to the economy and everything. And, if we didn't detect in time, if the traffic was not stopped, then a lot of people have died in the collapse. So this is all weird when we rely for such an important structure on the calculation of the frequency of failure, A frequency. So that's one part. So like I said earlier, if you look at the risk of consequence, close to $20 billion. If people died, if there was a traffic on the bridge, then we can't imagine what was the loss. But this is which will prevent the ship in the first place to going and hitting the bridge pier. Bridge pier had no problem. Bridge has absolutely no problem. It was a good bridge. The problem was that piers are not really designed to be impacted by large ship. And this happened. So if you look at the risk cost versus the mitigant cost, 6,000. Means you have really massive risk there that we failed to address. Again, I showed you this already, that if you have this kind of scenario, that you have a freak accident, that something comes and hits a bridge pier, are we willing to take the risk when our cost itself is so small compared to the risk that it will cause massive damage? So what do we do? Well, we have been doing work on bridge fenders. Any DOT will know that when we have a bridge fenders, we do this test. We crash testing. We do the crash simulation. My 10 years, last 10 years, we have done a lot of these crash simulations on bridge pier, truck impacting bridge piers, where we have developed the guideline, which is being used by Federal Highway and many of the DOTs on how to design bridge piers for impact. And this is very definitive that we can actually say this is our risk, 150,000 ton ship. And I want a performance, not necessarily by making the pier strong, but pier and surrounding, the fenders, the rock island, or whatever you can do around, which will not cost you so much, but it still prevent the ship from going to the bridge. And you can design that. So we started looking at how to do it. So last 6 months, we created this model of the ship, which is called, dolly ship. It's a Neo-Panamax type of container ship. It's a finite element model. It's not just rendering or drawing. It's a finite element model. We can vary the weight. We have tested this model for a lot of scenarios. This model has 38,000 nodes. It has 50,000 elements in LSDANA, if you know what is finite element modeling. And you can see the view, the front view of the ship, the elevation view of the ship, and this is the actual dolly ship that was there. We have also calibrated the ship model for different DWT all the way to 300,000 ton. Because right now, the biggest ship that we have in operation around the world is 600,000 ton, which is like almost close to more than 2.5 times of dolly. Now, can that ship come to the Baltimore port or one of the U.S. port where important bridge? Yes, absolutely. I mean, after Panama Canal modification and everything, if something passes the Panama Canal, it will come to Maryland port. And the naval trade is getting bigger. The shipping company, they are using bigger ships to carry goods. It's profitable for them. So these kind of ships, yes, is going to come. Our model, you can see here, this is the ASTO. This is our model based on Pedersen's result, which is the best possible result that you have in the literature right now. We cannot do certainly the crash testing of a large ship. We can only rely on the finite element modeling. But very good modeling, and the design of the ship is actually based on actual finite element details of an actual ship. So that gives us a lot of confidence. Just like you design a major bridge, you don't do crash testing. It's the same philosophy. Look at this ship when you impact the ship to rigid wall that, 95,000 ton, 145, 215, 300,000 ton. So as the ship comes and hits a wall, the bow crushes, and depending on what speed you are and what weight you have more crushing, and more crushing you have, the larger the impact force on the bridge will be. This is the impact force time history, that it goes like initially the front of the bow, you see this portion, this front of the bow will crush, and then the crushing will, extend through the bow. And you can see that, this all crushed, and you see this different peaks. They will come different parts. And, at some point when it's crushed completely, the force will. The ship will keep on hitting the pier or wall, and at some point it will come to rest, and the ship will recoil back. That's when the force goes to zero. Let's look at the picture of the ship. our computation model that it's, you have an imaginary wall that's it's hitting, and you can see how the ship is getting crushed with this imaginary wall. So you have rigid pier ship initial velocity 7 knots, 6.8 knots. That was the velocity of the dolly ship. You have the rigid pier. You can see center impact. So first this part will get impacted, then this part, when they get crushed, and then this part will start getting crushed. The peak force during the simulation is around 51,000 kips. But if you go to the ASTO code will tell you that just design this one for 30,000 kips. So you have almost order of difference. That the ASTO is telling you 30,000, the actual impact could be more than 50,000 kips. So that's the challenge we are looking at. See, close-up view of the pier, the damage to the ship. After impact, the ship is damaged completely. Again, dolly ship was side impact, so you can see the ship comes and impacts the pier on the side. You can see the damage here. I'll show you later on the comparison with the dolly ship. The damage is very similar to what really happened in the dolly ship. In this case, the force will be 46,190 kips, but if you go to ASTO code, it will be even lesser than 30,000 kips. So the discrepancy is much bigger when you have the side impact. So what really means in terms of protection of bridges, well, we applied this to a suspension bridge model, and this is an existing bridge model designed before the guideline for ship impact in 1991 came into picture. This bridge was built in 1960s, a major suspension bridge. We built very, very detailed model. Again, we didn't build this model now in this year. We have been working on the long span bridge for a long time. So this was a model that we had built previously. And this model is as if like you are building every element of the bridge. So, the deck or cable or everything is built as if we are taking the bridge into apart, and piece by piece we are building into the final model. A bridge basically replicates quite accurately the real behavior of the bridge. So this is the bridge, and what we do is we say, okay, this ship will go hit the tower at the center impact with the same velocity like dolly ship, 6.8 knots. And if we look at the tower, this is long suspension tower, this is the impact zone. After the impact, we get, this, the displacement, we say the tower will get damaged by 4 feet. Looks a big number, but the tower is very tall. So we go and, do the analysis of the tower with this, try to find the plastic rotation of the tower. Yes, tower is severely damaged, but the bridge is intact. It didn't collapse. Because the suspension-based towers, they are subjected to massive amount of compressive force. And the virtue of this compressive force, the sections are bigger, very big. They have a lot of shear capacities. On the other hand, key bridge, it was just supporting, the tower was just supporting the weight from the truss. So, the towers, probably piers were not as strong as the suspension bridge. The same goes for the cable-stayed bridge. So, and the next case we look at is the off-center impact, that, the tower is not really in the line of the ship, slightly away from the ship, like what happened in case of dolly. And then we do the analysis. And now you can see that this was the actual dolly ship, damage here. A lot of cargo is here. But if you look at the overall damage to the ship, again, we don't have information, just the pictures. Based on the pictures, and when we go into the finite element analysis, we can actually take the layer by layer and see how deep was the damage. We can see the damage in case of both the two are quite similar. We cannot calibrate exactly because these are the incidents where there's so much difference in impacts and all those things. But the damage is similar level like you have with actual dolly ship. That gives us confidence that yes, the simulation is quite realistic. And again, we have to design these impacts, not but factor of safety of 2 or so, but much higher factor of safety, because ships can vary in dimensions, stiffness, size, and all those things. So given that variability, we need to have some factor of safety. So what do we do? Well, there will be always a bigger ship. Look at the history, 33,000 ton GW for Sunshine Skyway to approximately 150,000 ton for Francis Key Bridge. Will this be the last one? Can we really limit the naval traffic? The ship operators to use a smaller ship? No. It's the economy of the size that they will keep on using bigger and bigger ship as long as they can make money. It's our job to protect the bridges, and we do, if the asset is too expensive, all we can do is, I say it like, look at the threat, which is improbable, completely improbable, what happened in Walton, what happened in Key Bridge, and if we can protect for that, cost is not that much. Your cost will be 60 million, you do more, it will be 70 million, it's not going to be $1 billion. It's going to be tens of millions of dollars compared to billions of dollars of damage that can be inflicted. What is the design philosophy? Well, not one thing. We design the bridge piers for minimum resistance because, there's no point in putting a lot of lateral resistance to the bridge pier. It's going to be unused capacity. We can deploy supplementary protection system from barriers, raised concrete platforms, islands, rock walls, energy absorbing fenders, a combination of these things. And we do this all the time. When we have for the trucks, we design fenders and we put the fenders around the piers on the highways to make sure the trucks don't hit the piers. So why can't we do the same thing for the bridge piers? And we have, at the point of the technology simulation, we can actually simulate exactly what you need. So we can develop a performance approach. In fact, all this I'm showing you is actually a performance approach. You can design for no damage, for low-level event. But if you have really, let's say, in future, a ship 2 times of weight of dolly comes, 3 times the weight of dolly comes, then at least you want is that your protection system will be damaged, but the bridge pier will not be damaged. Now, you can assess the performance with meaningful acceptance criteria. Why we say this? Well, long span bridges, a very high value, very high consequence. We can design maximum credible ship. There will be future increase in size, current capacity, and need to increase the capacity in the future. But one thing is, we need to guarantee the safety in absolute term. We cannot just say that probably this will happen because this structure is too important, that there will be loss of life, there will be massive consequences. And the point is, the consequences will be way beyond the cost that will be needed to prevent those consequences. And by the way, if you didn't know about this, the Dolly Bridge, the Francis Key Bridge, this was not the first time it was hit by a ship. In 1980s, the bridge was hit by a smaller ship, 7,000 tons. What really happened, and you might have heard the news that the bridge pier had some kind of concrete fenders around that. In 1980s, when that 7,000 ton the small ship hit the bridge, that concrete fender was all crushed, all damaged. That was a warning sign that this bridge is likely to be hit by a bigger ship. And these bigger ships have been coming for a long time. It's just that, somehow there was a complete loss of risk assessment, that there is a risk. The risk was always there. Somehow the risk was not assessed that a massive ship could come. There's nothing in the way to prevent the massive ship from hitting the pier. And the pier probably had only 7,000 capacity. They didn't survive. It was saved in 1980s because the ships were small. But now we have these ships which are 100,000 ton capacity, more than that. And bridge would not have survived. I can't believe that, when there was a maintenance done, this was not a knowledge that it was not there. It's just that there was no regular risk management approach where, you need, just like you do the load rating, you look at the bridge capacity all the time. Every 2 years, you do the load capacity. Why can't we do this? We have to actually develop approach where we look at the naval traffic, not 2 years, every 5 years, 10 years, you look at the naval traffic, look at your asset and see what is the risk of collapse to the asset. And if you see that there is a risk, the action needs to be taken immediately. With that, I'll stop and we'll be happy to answer any question. Thank you very much.
One question, we probably have time for just one.
Yes, sure.
So for all the bridges, how do you warrant that we need the concrete fenders or we need the concrete walls?
Well-
Or is it just for, we need it for all the bridges?
Well, like I said, if you look at my last slide, you don't really need a concrete wall everywhere. So, if you look at some of the bridges that I know that, now the people are working, you have Rock Island. Rock Island is very simple. You have, the bridge pier, you create this barrier and fill the barrier with the Rock Island, rocks. So when the ship comes, the bow of the ship will actually get stuck in the rock.
All right, so I'll just rephrase it. So how do you warrant it? So every bridge needs that protection around the pier, or do you warrant some criteria that, okay, this
Your criteria is very simple, that, if you look at the size of the ship that is coming and knowing that a ship can go, out of control anytime, there's a certain frequency, but you don't want to rely on that frequency. So what is the max size of the ship. And also, when you want to do repair, you don't want to do the repair for 5 years. You want to do repair for 10, 15, or 20 years going forward, that looking at the life of the bridge, that you want the bridge to survive and stay there. So if you look at all the factors, right, then, you take what you call is your maximum credible risk, and you assess the capacity, you assess the environmental of the capacity, and if you think they are safe, then you don't need to do anything. If you already have a protection, a Rock Island or fenders or something, then you don't do anything. But if you don't have those things, then you do need to, protect the bridge, take actions, because it's not like 10 years, nothing happens, means nothing will happen one day in the future, and you don't want to take risk for that one day in the future when that traffic accident might happen. Yes?
I have a question. As dictates about everything for the substructure, like pier protection, fender system protection. Do we look into the superstructure, spanning, or certain kind of superstructure will behave better in case of collision?
Well, let me bring to your question something else. So you have two kind of impacts on the bridge pier. One is when the ship might just come and hit the bridge pier, right? So you need to absolutely protect the bridge pier. There's another kind of accident which happened in China recently, that the ship was right in the channel, and the ship had something very high on the top, and it went through and hit the deck, right? And it cut through the deck. Well, we can't really do anything about that. Yes, we can do something, put some protection system before the bridge, so that when the ship is coming, at least you'll reduce the speed or minimize, something can be done. But superstructure-wise, nothing as such. But if I look at the simulation that we have, so when you have the suspension bridge, you have this tower, and when the ship hits, and you also have the cable. These cables provide lateral restraint. So if you just take the tower, the suspension bridge, and if you take the full suspension bridge with cables and everything, the suspension bridge with the cables and everything will give you larger capacity to sustain impact.
Because in the other case, there was not only one span, multiple spans fell at the same time, only one pier got hit.
That's a domino effect. It's a dynamic effect. If you lost one span, it's almost guaranteed that because of the dynamic shock and pull force and everything, that you have the complete dynamic instability in the system, where collapse of the one pier will guarantee lead to the collapse of the whole bridge.
If we have the
No matter what you had, unless you had the spans completely separated.
yeah.
And the piers completely independent, the one pier collapse, then only this portion of the span will collapse. If you had this design done carefully, they are okay. But if you had, the way we have the spans are connected each other, and we have the continuity and everything, that it's almost guaranteed that the whole bridge will collapse because of dynamic effect. But there's a major shock. When this pier collapses, there's a major pull to all the spans and everything in this direction.
Shouldn't we have some kind of, in those kind of impacted bridges, we have the span configuration like that should not be
Why not?
throughout the bridge?
I think it will be a lot more easier to just protect the bridge pier. We put the fenders or wall or something to make sure the ship does not hit the pier, and the pier does not go through those kind of very massive impact forces, because there's no way you can design those spans for those, the connections and all those things for massive impact forces. A lot more cheaper will be to just not design the bridge pier. I'm saying it's the peripheral system around the bridge pier. So the whole environment there, whether it's a channel depth or rock island or whatever you do, the whole peripheral around you do such that the ship does not hit the bridge pier. That's the goal.
Thank you. I don't think we have time for any more questions here. We're a little behind, but
Okay,
Dr. Agarwal, thank you very much.
Thank you.
Okay, our next presentation on sustainability and resilient infrastructure systems will be presented by Indira Prasad. She is the Associate Director for the City of New York's Transformation and Change Office and is currently pursuing a PhD in Civil and Environmental Engineering from Stevens Institute of Technology.
Hello, good afternoon, everyone. I hope all of you are doing good. It has been a very long day, and thank you for being here. And I am excited to discuss sustainability and resilient infrastructure and how we can navigate the future with technology advancement like AI, which is artificial intelligence. Imagine a world where our infrastructure anticipates and withstands the challenges of climate change. That is the future we are building with AI. This critical topic has many fascinating aspects, and let us dive in. Oh, sorry. Sorry about that. Here is a very high-level agenda, presentation agenda. We will look at the definition of infrastructure just to understand also critical infrastructure and causes of failures, infrastructure resilience and sustainable development, innovation, technology and infrastructure, America's infrastructure and ASCE's rating scorecard, and life cycle principles, risk management process, AI in civil engineering, and research gap that I have analyzed, and also how we can harness the power of AI for better tomorrow, and finally my recommendation and conclusion. So let us decode what is infrastructure. Infrastructure is essential physical and organizational structures and facilities actually needed for a society or enterprise to function. Also, these structures support our day-to-day lives and shape humanity's direction. They provide foundational services critical to society and human. They also are the foundations of the economic activity and our quality of life. Infrastructure can be classified as critical infrastructure and non-critical infrastructure. As you can see here, critical infrastructure is a body of systems, networks, and assets to essential, and their continued operation is required to ensure national security, public health, safety, and economic security. According to PPD 21, we have 16 critical infrastructure sectors. This has been identified. This is really vital for our nation, which is listed here as chemical sector, commercial facilities, communication sector, critical manufacturing sector, dam, emergency sector, energy sector, information technology, government facilities, healthcare, transportation, water and water resource sector. So let's take a look at it, how critical infrastructures causes failures. So the analysis shows that we can categorize into below basic groups. First one is climate-related threats such as floods, hurricane, and extreme heat, and geological earthquake and landslide, etc. could cause also disruptions, and biological threats like pandemic like COVID-19, and technological threats like communication failure, equipment failures, etc. And the criminal threats such as terrorism, cyber attack, and artificial accidents. All these could cause disruptions. So this slide, I have captured the disruptions to critical infrastructure parameters reduces performance. That means you can see, as shown in the figure, performance decline is inversely related to the emergency intensity and the infrastructure elements resilience. So here, the effectiveness of resilient infrastructure pivots on its ability to anticipate, absorb, or rapidly recover from disruptive events. And resilience ensures the continuity of services despite disruptions. It also depends on the contingency planning and effective infrastructure design. And this figure shows infrastructure resilience wheel. Actually, this illustrates that infrastructure resilience wheel highlighting critical components for resilience, including good governance, information flow, robustness, capacity to learn, resourcefulness, flexibility, responsiveness, redundancy, and safe failures. So, resilient infrastructure, what does it mean? In summary, resilient infrastructure has 4 primary characteristics, which are resistance, reliability, redundancy, and response and recovery. What is resistance means protection against anticipated events and shocks. Reliability means components designed for various conditions. Redundancy incorporates backup plans. And response and recovery means if anything happens, rapid response to disruptions, ensuring public safety is the primary goal for us. So this slide shows the lack of resilience infrastructure, how it harms the society and firms. So unreliable infrastructure leads to significant disruptions and cost. These disruptions directly impact human well-being, business, jobs, and income. This figure illustrates how natural hazards and shocks affect infrastructure impacting communities and firms. So next, let's take a look at the infrastructure dependencies. Infrastructure dependencies are very complex, making risk mitigation challenging. Most infrastructure elements heavily depend on power and communication network, as we all know, and their failure would be dramatically impacting local and global economies and society as a whole. So critical infrastructure functions as a system of interrelated systems. For example, transportation, public safety, and public health are all interconnected and interdependent. For example, I was with MTA, New York City MTA, during the COVID-19 time, and I know that we all worked for days and days to make sure that the transportation is still running. The subways are still running because we had to transport the healthcare professionals. That was a very good example. So what is mean by sustainable infrastructure? Sustainable infrastructure refers to infrastructure projects that are planned, designed, constructed, operated, and decommissioned in a manner to ensure economic, financial, social, environmental, and institutional sustainability over the entire life cycle of the project. That is the key here. We are not looking for the short term. So here I have captured how the sustainable development and sustainable infrastructure, how they are related. So sustainable development is grounded in 5 dimensions, and sustainable infrastructure actually supports sustainable development. So if you look at the 5 dimensions, they are people, planet, prosperity, peace, and partnership. So social, economic, and environmental impacts must be considered for sustainable development. It's really important. These lead to balanced trade-offs and spin-off. In essence, resilience infrastructure is the backbone of sustainable development. Next, if you link this United Nations Goal 9 and Goal 11 are directly related to building sustainable and resilient infrastructure. Goal 9 actually guides us in building resilient infrastructure, promoting inclusive and sustainable industrialization, and fostering innovation. Goal 11 actually promotes making cities and human settlements inclusive, safe, resilient, and sustainable. Next, let us take a look at how innovation and technology affects the infrastructure sector. So investment in infrastructure of innovation drives economic growth. With over half of the population prefer to stay in cities, and mass transit is really vital. The figure shows passenger kilometers by rail from 2007 to 2020. Data exceeded 30 billion until COVID-19, and which caused it to drop by more than half. Now we are back to over 35 billion, surpassing the pre-COVID levels. So this shows that it's really important for us to invest more in public transportation. So this slide, I captured the cycle of critical infrastructure. Resilience is a cyclic process which involves prevention, absorption, recovery, and adaptation. Prevention means we should try to prevent it. But if we suppose certain cases prevention is not possible, then we should be able to find possibilities for absorbing that disruption. And once the absorption is also not possible, then we have to look for the recovery steps. After the recovery, then we have to adapt and try to see the design changes or whatever we could do so that the next time when it happens, we should be able to prevent it. So it's kind of a cycle process. So this next two slides, the following two slides will highlight how technology and innovation shape the transportation industry's future. Technology enhances rail safety and efficiency. PTC, CBTC, smart sensors, automatic investment equipment, etc. are just a few to mention. This particular slide captured 9 most impactful innovation areas for the rail industry. That is artificial intelligence, that's the latest topic everywhere, and automatic train control, smart sensors, predictive maintenance, cloud computing, drones, biometric ticketing, information, Internet of Trains, and big data. These are the revolutionizing technology especially for a rail industry. To foster sustainable growth, cities must prioritize expanding public transportation, mass transit development. Actually, especially metro and light rail projects are really crucial for sustainable urban growth. If you look at closely, rail is the most attractive option for a transport corridor. Population growth and the growing number of middle-income families who cannot afford to live in the city center make rail transport more desirable due to ease of accessibility, reduced travel time, improved quality of life, and reduced environmental footprint. Most of our existing infrastructures, as we all know, including transportation, is not sustainable and resilient. Every year, ASCE, American Society of Civil Engineers, publishes an infrastructure scorecard for America's infrastructure. According to the latest report, America's infrastructure has a grade of C-. So you can just imagine how much more we have to go. We have a long way to go. For example, 43% of our public roadways are in poor or mediocre conditions. The graph actually shows that the condition of bridges rose pretty far from good to fair. Almost 300,000 bridges are in fair condition and is growing. This graph actually emphasizes the importance of periodic maintenance. Reduced maintenance reduces the asset service life. If we must extend the infrastructure's service life and resilience, we must inject funding for maintenance and operations. And if we have the capital funding, of course, we can even add on to the advanced technology, and also that will extend further the service life. So here I just want to touch the risk management process here. The following two slides capture the infrastructure risk management process. A risk board diagram is a tool for risk assessment and mitigation. It is crucial to take precautions for preventive controls. If we can prevent it, we should identify them prior to that. But if the events are uncontrollable, then we should find out a mitigation strategy for events beyond our control. So this tool is very useful for identifying risk. This is a sample risk matrix. We capture the events based on likelihood and consequences and determine the severity of the situation so that appropriate action can be taken. Optimizing resources and funds are always been challenging, as everybody knows. Fund is always limited. As shown in the figure, with an unlimited budget, there is a balance between performance, life cycle, and safety. But if the if the funding is limited, then we are going to give priority for safety. over performance and cycle cost. So I would like to just touch base the research gap. I would like to mention that I am just a first year student, a PhD student. So I've just completed my literature review, but I would like to share what I am currently intend to do. So my research is focused on climate change impact on critical infrastructure and how we can harness the power of AI to build and maintain sustainable and resilient system. So if you look at this graph, a surge in artificial intelligence studies in civil infrastructure between 2000 and 2021, which shows that growing momentum in the field of infrastructure. This suggests that AI's roles will expand in the near future. Even when I'm doing the literature study, I don't find that many articles or research papers that I can use it. It looks like I may have to dig further, or I have to find my own ways based on my professional experience and industry experience. So artificial intelligence actually mimics human intelligence by analyzing large amount of data to find patterns and predict future states. While AI generates insights based on existing data, human intelligence can invent new concepts showing emotional understanding, empathy, and complex social interactions. So we have to use both. There's no way that artificial intelligence is going to replace human beings. So that's not going to happen because we still have to be in the middle. So let us glimpse how an AI-based decision support system functions to reduce climate-related impacts on the infrastructure system. AI can handle a mass amount of data from multiple systems, such as GIS, GPS, IoT, sensor data, and intelligent transportation system, weather system, etc., risk and mitigation data, and so on. But the most challenging aspect is we have to integrate all these systems together and integrate them into the AI system to create a pool of data. So then AI will be able to help us with the decision-making aspect of it in a very quick manner. Humans may take weeks or months, but AI will be able to do it in a very short time period and also very efficient way. So here is an image of Auckland Harbour Bridge during a tsunami that shows the impact of high waves. AI can predict natural disasters like hurricanes, earthquakes, floods, wildfires, volcanic eruptions, and fires. And of course, if we know something is coming on the way, we can take absolute precautions. So this is a great features that AI has. And AI revolutionized civil engineering field by enhancing the design and simulation process. It has several features that help us reduce the impact of climate change on infrastructure. For example, enhanced predictive capabilities, early warning signal, dynamic traffic management, improved risk assessment, real-time monitoring and adaptation, improved safety, efficiency, asset management and maintenance, optimize maintenance operations, cost efficiency and resource optimization, climate resilient and optimized design and construction, resilience planning and decision support system, and automation of inspection. So my research question is, what are the primary climate change factors affecting civil infrastructure? How do these factors impact different types of civil structures? How can AI-driven techno-economic solutions mitigate the climate-based impacts on civil infrastructure, particularly for cost efficiency and sustainability? I will be using both quantitative and qualitative data for the hypothesis testing and exploratory analysis. Data collection may be in multiple ways: historical climate data, infrastructure performance data, broad range of past events and their impacts, feedback from infrastructure professionals and stakeholders interviews, case studies, and surveys. The impact, what I'm expecting from my study is this research will offer invaluable insights and enabling policymakers and infrastructure team to design and maintain sustainable and resilient systems with greater efficiency and effectiveness through the strategic application of AI. As a policy maker myself, I know that we have a greater role here to play. especially in shaping sustainable and resilient critical infrastructure. We need to build the policy measures needs to be, we have to create, connector vehicles. I know that I was part of that, even for the congestion pricing projects for the MTA. I was part of the policy making discussions. So I know it's really challenging. Different scenarios needs to be considered. And we want to make sure that we create a robust system and robust policies are there. And also information flow should be transparent and smooth. And communication and collaboration with multiple stakeholders are really absolutely required. And mobilizing finance is everything. And so we need to make sure that we have enough finance to implement it. So the recommendations from my side is get the fundamental right. That is, get the basic right. That means enforce regulations, construction codes, and procurement rules. This is really important. And building institution for resilience, and create regulations and incentives of resilience, and improve decision making, and finally provide financing. So in conclusion, sustainable and resilient infrastructure is essential for enhancing our quality of life, protecting vital resources, and driving economic growth, while the journey to developing sustainable resilient system is really complex, but the rewards are substantial. And building resilient infrastructure and fostering innovations are essential for our future. Today's efforts lay the foundation for tomorrow. Let us harness the power of AI to make our infrastructure smarter and more resilient. And word of thanks to NJDOT professionals and everyone else who actually helped us to organize this event, and my advisor, Professor Bo, and my mentor, Dr. Prasad from NYC DOT, and supporting members, Janet, Ran, and Sean. Thank you so much.
All right, thank you, Indira.
Thank you.
All right, and our final presentation of the day will be on cost-effective pavement management systems for municipalities in New Jersey. The presenter is Dr. Surya Swarna, who is a research scientist at the Center for Research and Education in Advanced Transportation Engineering Systems at Rowan University.
Thank you.
Good afternoon. Can you hear me well? Yeah, perfect. Dr. Mehta couldn't make it, so I'm presenting it entirely. So thank you so much for giving me this opportunity to present our real-world solution, cost-effective payment management system for municipalities in New Jersey. So in New Jersey, we have a total of 564 municipalities, and New Jersey have a total road network of 39,000 miles of road network, out of which 26,000 miles are managed by municipalities. And for managing this roadway, they get about like $150 million as a municipal aid, and for counties it is about $160 million annually. It varies. And the work criteria for this particular municipal aid and county aid is based on the existing condition, based on the safety, and also the traffic volumes and so on. But the municipalities have to spend significant amount of this municipal aid or county aid to do the data collection, how their roads are, like what is in bad condition and what is in good condition. So the current data collection system that existing in New Jersey, like many contractors are using it, it is LiDAR, so which costs about $150 to $400 per central lane mile. And if we collect the data and also analyze it and give recommendations on maintenance, it costs about like $350 to $800 per central lane mile. So in several cases, these data is mostly like a kind of manual, and also there is no map visualization for the entire road network. So, and also like for certain small municipalities, they don't have funds to do this data collection. So they depend on complaining strategy. So whoever is complaining, what neighborhood is complaining, they will repair their road first. And some of the municipalities, if they have a little budget, they'll send some crew crew to the roads, and they will ask them to collect the data, like how many potholes are there, how many cracks are there, how is the road condition. So for doing this manual data collection is also kind of safety risk. So we came up with a solution that is based on AI. So we are simply using a cell phone to scan the entire roadway and give the payment distress. So it is quite affordable. As it is a phone, you can attach it to any vehicle. If it is like municipalities can attach the cell phone to garbage trucks, which goes every week. So it will automatically scan the road, and it collects the data, and it actually gives everything on a map, like how is the condition. I'll explain like how we came up with this solution and stuff. And we are expecting to reduce the cost of data collection by about 90%. We are at about 80%, like because of the cloud computing and stuff. So we are trying to target it to a 90% cost reduction. So this is the cell phone that we attach to our. This is our Rowan truck. I'm from Rowan University, so we have a truck, and we attach that phone to the end of the truck at 60-degree angle, so that like when we are driving over a roadway, we can drive at any speed. We can drive at 60 miles per hour, 50 miles per hour, up to. So when we are driving, so it will automatically record a video of that particular roadway. So it covers about like 12 feet lane. And it actually, we use some AI to detect the distresses, and it will populate all the distresses on a Google map. So if you click these red spots, it will automatically show these pictures, like where is the roadway, like what is the distress existing in that particular roadway. So the major reason for having this cost effective, and that main advantage is we can do it multiple times in a year. So we don't need to worry about like doing it couple of years, because the cost of data collection is quite less. So we can collect it multiple times, and benefit of doing multiple times is we will also know which one is getting deteriorated faster. So based on that, we can allocate some fundings for future to repair those roads. And also, or else we can preserve some of the roads, like instead of repairing reconstructing an entire bad road, so we can kind of allocate that funds to preserve some of the roads that are getting bad, and then we can repair the bad one in later stage. And another advantage of it is like it gives a visualization, so it actually shows you where are the distresses in your particular roadway. And here is how we developed it. So initially what we did is like we actually attached this phone, and we recorded the videos of each and every roadway in a municipality. We tied up with the Borough of Collingswood. So most of the research that we did in Collingswood. So we recorded a video of roadway, and we attached our GPS coordinates to it, and then we used some models, like the developed models, AI models, to detect the distress in images, and then we developed a PCI model. So we use that PCI model to come up with the PCI. So I will go step by step. So there are 3 phases in total. In the first phase, so we initially collected the data. Data in the sense like video data. So we divided that video data into frames. So for example, if we are driving at 60 miles per hour, for every second we are getting about, 60 frames. Yeah, 60 frames. So it is covering the entire roadway, like even if we are driving at 60 miles per hour. So after dividing it, we manually labeled each and every image, whether it is having a pothole, crack, or payment marking, or else any obstacles like maybe leaves during the fall season, all those stuff. So once we labeled it, we trained our AI to detect each and every distress on the pavement. And then we trained it to get a minimum accuracy of 80%. So if we don't get the accuracy, we again gave more data to it, and then we retrained it. And once we have achieved like 80%, we use that particular AI model. And in the phase 2, we developed our PCI model using this AI data. So similarly, we went to the road network, we collected the data. We used ASTM standard to determine the PCI of it. Similarly, for the same data, we actually used our artificial intelligence model to come up with number of images that has potholes, cracks, and all these images. So based on that, we developed a regression to come up with our PCI model. So we used, in the phase 3, we implemented it in Collingswood. And in the last stage, we went to all the roads. We collected data for all the roads, and then we used our AI model to detect number of images that has potholes and cracks. And we used PCI model to come up with the PCI of that particular roadway. And then, in the end, based on the PCI and the distresses, so we came up with a road maintenance strategy. And this is that whole data collection. So we collected about 54,000 images, out of which 17,000 images we collected manually. For example, if we have a pothole, so we are like the actual phone is looking at 60 degrees angle at a certain height. But sometimes it may not look like that. So that's why what we did, for a pothole, we took an image in different directions, different angles, and different conditions. If it is wet, it looked differently. If it is dry, it looked differently. So we kind of manually collected all those different conditions so that this AI will be, we can implement it any condition, any pavement condition. And also we have 36,000 images that is collected directly from the municipality using the AI. And then the phone resolution that we used is 2K, and also the frame rate is 60 frames per second. And angle 60 degrees, the major reason for 60 degrees is to collect 12 feet of roadway. And GPS coordinates, we are collecting it to every 200 milliseconds. And all these frames are attached with the GPS coordinates so that it can accurately show where the distress is on the map. So we use different architectures. All these are AI architectures. So out of which, like, we came up with the best AI model, and then we use that for our analysis. And then in the development of PCI model, so we collected the data and we detected these diseases: transverse cracking, longitudinal cracking, alligator cracking, and potholes. We are trying to get more distresses as well, but for now we have only for these 4 distresses. And then we use ASTM standard to calculate the PCI. And then by using the AI output for the same roads and same roads with ASTM standard, we developed the PCI model. This is how PCI model look like. So it is a function of a number of images that has potholes and cracks, and both. And when we look at the accuracy of this model, so we collected different roads, right? So we manually calculated it, and then we estimated the PCI using AI. When we look at the accuracy is too high. So then we had a thought, is it a generalized model? We will say definitely no. The major reason is, as this data is mostly developed based on Collingswood, this is applicable to Collingswood, but there are some uncertainty in terms of pavement conditions. Because when we go to other boroughs or Collingswood, we found they don't have proper lane marking. They have moreover cracking instead of potholes. So because of this inconsistency, this model is not applicable for Collingswood. But we made an effort to retrain our AI very easily by collecting the data in new municipality. So calibrating this model for different municipality is kind of easy. And this is how it works. So basically, we have a cell phone, we have an Android application that we develop. It will be installed in that cell phone. We will simply attach it to a truck. We will drive over all the road network in any municipality. So once we drive over, so it will automatically collect the data. So it is kind of video data. And there will be a simple image processing technique in the cell phone itself, in the Android application. As cell phones cannot really compute much compared to the servers. So we simply use a basic model that is good road, bad road technology. So how it works is, it will scan the roads, what the frames that application got. So it will divide it into two parts. One is good roads and bad roads. It is a basic application. If there is no distress at all, then it will consider it as a good road. And if there is something, it can be a pavement marking, it can be a distress, it can be anything. If there is any obstacle, then it will consider as a bad road. So this application will delete all the good roads and take all the bad roads to the server. On the server side, we have the AI algorithm to detect the potholes and cracks. So using those detected potholes and cracks, we will determine that AI will determine the PCI, and it will populate on a Google map, on a heat map. If it is distress based, if it is PCI based, it is a line map. And then the output that we get out of it is a ranking of the roadway. So out of the entire network, which one to repair first and what is the maintenance recommendation for it. So that is the output we will get. And then this is the Android application that we have. It simply records it, extracts the data, and it will send all the bad road images to the server where the entire AI thing goes on. This is how heat map looks like. So if there is any big distress, so that will show up in a red color. If it is good, then it will show up in a green color. If it is a PCI, it is a line-based. Like there is specific designation for example, if the PCI is between 60 and 70, there will be a red line or different lines. And the future work, so we have kind of came up with a really good system till now, and we are trying to improve much further. So we are trying to improve and maintain the accuracy of AI model. So we are creating a feedback tool. For example, I mentioned like the accuracy that we are targeting is 80%, right? So if the probability of having a pothole, if it's say 79 or 81 near to 80, so what it happens is the AI will send us a message, okay, this particular image we are detecting and probability of having a pothole as 80%. So is it really having? So if it have a pothole, we can give a feedback to AI. Okay, so it have a pothole and we can highlight the pothole as well. Based on that, the AI will automatically retrain itself and gives a better result for future. And then we are trying to include more distresses, more distress types into the system. And also, if you observe, most of our AI depends on number of images that has pothole and cracks, not based on severity, which is one kind of limitation in our study. So now we almost like implemented it, but we are working on YOLO technique, which actually detect the distress, its type, and also its severity. How deep is it? How deep is the pothole? How big is the pothole? What is the area of it? If it is a crack, how long is the crack? So it is able to detect all the severity of each and every distress. And also we are trying to automate our Android application to collect everything by itself and gives final output instead of we interrupting somewhere in between. And we are looking at different distress indices. The major reason for this one is we are currently using ASTM standard, which is like national standard for determining the PCI. And the detect values are kind of national standards. So we don't have anything specific for New Jersey. NJDOT currently use SDI for their payment data, payment condition. So we are kind of leaning towards SDI and also PSCI to come up with a better model. So this is how our AI research going on. I would like to acknowledge all of our team, majorly our undergrad students who went to most of the roads and they collected the manual data and they labeled it. They did a lot of work. You saw, right? It is about 54,000 images. Like taking 54,000 images and like labeling each and every image is a very big effort. I would like to thank all of our clinic students to do that. Thank you so much.
Okay, so we do have time for questions if there are any questions since this is the last session. Okay, looks like we got one right here.
Yeah.
Do you guys looking like any management system that we have like a safety management system or bridge management system. Do you guys making any municipality management system for the roads? So they can use it, like you say, you separate it out, the bad and the good one. If you putting the good one at the last, let's say from 100 to 1 to 100, it will be the good one, but 1 will be the worst. So once you take out 1 to 50, then maybe 100 become another 20 by the time.
To be honest, like municipalities are not interested in that first. They just need which one to repair first out of their entire road network, because they have to show it to the neighborhood that they are making some effort to repair the bad roads first, because they are getting complainings from all the roads. Even if there is a small pothole, there are some people who are complaining a lot, right? So instead of like looking at that one, like if they have some kind of scoring throughout the road network, they can show it to people like the community and say, okay, there is much bad roads, so we want to take care of those first.
Because I work in a local aid and we give the grants to the municipalities.
Okay.
That's what I'm saying, because we give the grant every year.
Yes.
So if they have the list, they know, okay, we got the grant for first 2 roads for 2 years.
Yeah.
Now we can go to 3 and 4. So that will help you to reduce your work again and again if you have that list.
Yes.
And are you guys considering when you go in the field, like a safety, let's say, can you incorporate the police crash record into particular that road? Because severity is also important. Let's say there is a pedestrian accident over there.
Yeah.
And you see there is a lack of lighting or lack of crosswalk or lack of signage there. So once the municipality put their application, they can put it, okay, we want to put the sidewalk here based on the whatever the management system.
Yeah.
Because say the severity is higher as well as the road condition is also bad too.
Yeah. So we put effort into the roadway only. We didn't really consider any of the safety risks. But the request that we got from Collingswood is they want us to look at the curb condition as well. So our current AI, like we almost developed it, we didn't release it yet. So this particular AI that we have now is kind of taking the roadway condition and also the curb condition. And in terms of safety, we don't have anything yet. So, but that's a very good idea. We will definitely look into it.
For
Yeah.
the future research or something, if you incorporate the safety, that would be benefit to.
Sure. Thank you so much. Yes, Robert?
Sorry, great presentation.
Thank you.
I'm very interested in this technology moving forward. There was a German company that came over and had presented their product to us that they had developed in Elko, and they were constantly improving it.
Okay.
One of the issues they had though was the system or the cell phone wouldn't work as well greater than speeds of say 40-45 miles an hour. How have you guys kind of done any work to validate that the speed doesn't affect the quality yet, or you're still in the process of, and if you did figure it out, how did you overcome it?
So we did figure it out. Like, so what happening is most of the images are kind of getting blur at higher speed. But what we tried is like we took that blur images and we tried to unblur some of the images. So there is some kind of machine learning technique to unblur those images. So we figured it out. So we tried at 65 miles per hour maximum at New Jersey. So we tried. We got good results with that.
Well, I'm interested in doing work with you in the future.
Yeah, sure. Thank you.
This could be a significant cost savings to pay.
Yes.
I mean, significant, as you know, we spend a lot of money each year, vehicle maintenance, vehicle calibration. The other part of the equation is IRI,
Yeah.
and I don't know how accurate and if the feds will accept that as a, going forward yet, but I think there's great promise in it.
Yeah.
You mentioned raw data too, so
Yeah.
that's why my one of the questions was that if a good image doesn't have crack but has running, is getting deleted directly.
Yes.
Monitoring the running.
So
That's what we consider at NJDOT to resurface or have a treatment.
Yeah, at this point of time, some of the images are getting deleted, some of the images are still there. The reason is like how it will show up. Like for example, the basic algorithm actually considers, okay, if the roadway is clean, okay, it will consider as a good road. Sometimes even if the rutting, it shows as a clean. But if there is like kind of shoving or something, like it will show up as a bad road. but we are kind of improving that.
Would the designer have access to these images? Like, we do
Yes.
quality control. When we look at SDI data, we see the images side by side to have our perspective of what we're going to rate it as.
Yeah.
Would we have with this
Yes.
designer to get to see the images side by side of your?
Yes. So if you see in my presentation, I have shown one particular. So here you can see the red spots, right? So these are the distresses. When you click that particular red spot, it will pop up like this image. What is the distress there? Exactly. Yes.
So, forgive me if I'm misunderstanding something, but could that camera be put on the side of the vehicle and observe pedestrian infrastructure as well?
Yeah, so we are trying to do a similar kind of thing. So we can do that, to be honest. We can definitely do that. Right. But the main problem that we have is at 60 miles per hour, it may not capture all those, okay, right, at higher speeds. But if it is a lower speed, it can capture, yes.
And so conceivably, theoretically, it would be possible to do this kind of surveillance work on pedestrian infrastructure to determine both its condition, its existence, how it's utilized, so forth.
Yeah, so to be honest, like all this technology we have already patented. Right. So now we are currently working on patenting another one, like kind of sidewalks, okay, condition of the sidewalks. So we are almost done with developing our system. So once we have it ready, like to be honest, like we have a very basic one. So once we entirely develop it, like we will patent it, and then we will come out and do that.
Fascinating.
Yeah, thank you.
Last question.
Yeah.
Since you are looking only images, right now you don't have any data related with the dimensions of it, right?
Yes, exactly.
Working on the future work.
Yes.
So the prediction of PCI right now is actually you are putting it in like 80% good.
Yeah.
But once you have those dimensions available, then you can use the distress manual.
Exactly.
You will have a good value of PCI.
Yes, exactly. That is what we are trying, like because severity plays a significant role in determining PCI. So that's why we are making our every effort towards getting severity of the distress itself. Yeah. Thank you. Yes.
So I'm in roadway, and in roadway we have straight line diagrams, and inside them we have video logs of our entire road that goes through all our interstates leading up to them. Can these images, can they be inserted somehow into our software when you have it finalized?
Sorry, can you repeat?
So these images that you're recording,
yeah,
in snapshots every however X amount of feet, can these images be uploaded or somehow merged into our DOT roadway straight line diagram, video logs?
That's a little tricky, but I need to think of it. I'm not sure. I'm not 100% sure about it. But most of these images, like we currently have a very small server at this point because this is still in the research stage. So we have a small server, like as soon as we get new data, we delete old data, to be honest. So that's why once we come to a full-fledged system, then we can definitely do that. Yeah, thank you. Thank you.
All right, thank you. That concludes our breakout session for today. Thank you to all of our presenters, and thank you guys for joining us. Take care.